So I told already, I tried to interpret that one already. Suppose if you have a light source here, and if you held, so this is the area, okay. Suppose take light source, light rays are your field line, isn't it? Light rays will also behave in the same manner, am I right? So just like, so you have a point charge, electric field will diverge from the point charge, am I right? So similarly, if you have a small point light source, your light rays are going to diverge, isn't it? So now, yeah, so can you see any simulations? Yeah, let me share it later. Okay, let me share it later. So there are a lot of simulations on that one. You can see. So one is, yeah, I have a light source here. You can see its shadow. Am I right? Whenever I put one light source here, you can see its shadow below. That shadow talks about, I mean, those light rays are obstructed by the area, isn't it? If there is minimum shadow, that means not much light rays are obstructed by the area. If there is maximum shadow, then obviously light rays are piercing this area. That's why, again, it is not passing through that area. That's why you have a large shadow, isn't it? So now look at here. So number of light, if I put a point light source here, number of light rays passing through this surface area. So that is one thing is that should be proportional to this area, isn't it? Let me take one planar area. Let me take vector field. Okay, let me take vector field, and let me take one plane area. So one plane. Is that okay? So now number of vector field line passing through this this area, planar area. Let me take planar area. Okay. And one more thing I have to take here. Yeah. So let me just see. One more thing I have to take here is idea is our field lines are almost constant, okay. If they are not constant, you can't add up, am I right? So if they are variable throughout the region of that plane, then what you have to do, you have to integrate actually, isn't it, to find total flux. For a time sake, let me assume I have a uniform vector field, any vector field. Electric field is our discussion, and I have a what you call planar area. So now, when I have a source here, so your light rays will fall on this one. Number of light rays passing through this one, that is proportional to, I can't count that one, isn't it? Number of light rays. I can only talk about proportionality. Number of light rays passing through this one, that should be proportional to area, obviously. Am I right? If you increase the area, number of light rays will increase. Am I right? Number of light rays is proportional to area. So we call that one as flux. Is that okay? That proportionality factor, we call it as flux. Flux is proportional to area. Okay, magnitude of the area. So later we are going to construct area as a vector, isn't it? Later we are going to construct area as a vector. And that is also proportional to, remember, I told one idea, whenever field strength is more, you have to draw more number of field lines, isn't it? That's one of the way. So suppose here, if I have charge Q, you may draw field line like this. If you have a charge 2Q, you have to draw still more field lines. Not only in this direction, in all direction. Are you getting my idea? So if charge is increased, obviously field strength is increased. Am I right? How do you show that increase in the field strength? By increasing number of field lines, by increasing density of the field lines. Is that okay? So that's how you have to show. Now obviously, so when you increase the strength of the field, what would happen? So suppose if you are increasing the intensity of this light source, suppose if you are talking about, then more number of light rays are going to pass through this one, and obviously then also flux is more. Am I right? That's why flux is proportional to, let me take electric field as my vector field, magnitude of that one also, isn't it? Not only that, yeah, it is proportional to magnitude of the vector field. Magnitude of the vector field will talk about how many lines are there, okay? What is the density of the field line? Is that okay? If magnitude is more, density of field line is more, so more number of field lines are passing through that one. What we are having here, flux is proportional to, so flux is a measure of how many field lines passing through this area. Is that okay? That depends on magnitude, obviously, because magnitude will decide number of field lines. Is that okay? So now area, obviously if area increased, it will increase. Not only that, some cos of the angle between them. Now I have to define theta, because look at here, I have same area, same strength of the field or light rays here, okay, but it depends on the area, am I right? So suppose if I held it like this, you will have a maximum shadow here, isn't it? If I held it like this, I have a light source here, you will not have any shadow. That means your light rays are not puncturing this one, isn't it? So that's why it should depend on some relative angle, am I right? Now our idea is to construct one vector perpendicular to the area, okay? Now you have to ask one question, okay? So I mean that's what we call that one as area vector, am I right? Area vector, it is always perpendicular to the area. Now if I take this is planar area, so now area vector will be like this, okay? Area vector will be like this. Suppose if I held it like this, so now my chalk piece direction, it's a area vector direction. Now light rays will also point in the same direction, cos 0, 1, maximum flux, isn't it? So when I had this one like this, look at here, your area vector which is perpendicular to the surface of the area, so which is perpendicular to light rays. So if my point source here, is that okay? So then your flux is 0, isn't it? Cos 90. So now this the relative angle between this area vector and the vector field. What is area vector now? So I mean that's our construction, remember. So to define this thing, to explain this nature, it's our construction. It's a imaginary area vector. So it's an imaginary vector, so which is perpendicular to surface, whose magnitude is area itself. Area vector is an imaginary vector perpendicular to the surface, whose magnitude is area itself. Is that okay? So now cos theta does matter, am I right? Suppose if you held this one, what you call like this, suppose if you are holding your plane like this, am I right? With area vector like this, and your electric field is like this, is that okay? Then what would happen? Electric field lines are grazing that one, they are not piercing into that one, into that area, isn't it? So that would happen. In that case, again, theta equal to 90 degree, your flux equal to 0, number of field lines passing through the area equal to 0. So now, so combiningly, what I can write now? I mean, so we will not take any proportionality constant, we will make it equal. So actually I have to write flux equal to this one, okay? Actually I have to write flux equal to this one. Then I have to quote that this is proportional to number of field line passing through the area. Is that okay? This is proportional to number of field line, so passing through the area, like that. Is that okay? Now look at here. So how do you write now here? E dot area vector for a planar area for a uniform, so what you call field. So now suppose again let me take other situation. The situation is, suppose electric field may be varying or area, so area may be a kind of curved one like that, okay? Let me take that situation. I have a curved surface area, is that okay? And my vector field is varying, okay? It's not uniform vector field, its strength is also varying, is that okay? And its directions are also varying, is that okay? Let me take like that. Now I have to find flux of that kind of vector field line through some curved surface area. Then what will you do? So you have to do surface integral. To before going into surface integral, what would you assume? You have to take one elementary surface area. You have to take one elementary surface area. Obviously, your area vector, I call this one as dA vector. I call this one as dA vector. Okay, that's always perpendicular to that small patch of area. Am I right? So then maybe, so it at this point your electric field will be in this direction. At that point, okay, at that point. Now take the dot product between electric field and that small area vector. What will happen? That the flux through that small area vector, isn't it? Flux through that small area vector. So that is, I can call it as d phi, small amount of flux through the small area. So total flux, so through the surface, so I mean over the surface, our total flux, flux of field line passing through the surface, that's nothing but surface integral of We call this one as surface integral. E bar dot dA bar. Is that okay? Now throughout the surface, so look at here, electric field strength may change. Electric field and dA vector, this angle may change. So everything should be taken into account, isn't it? Earlier what I have taken? So I have taken uniform vector field. That's why it was very easy to calculate the flux. Is that okay? So if you have a planar area, if you have a uniform field, then you can just use this one. Am I right? So, but if you have a non-uniform surface area and non-uniform field, then you have to go for surface integral. We call this one as surface integral. And that's a scalar. The result is a scalar. Can you just write one more sentence here? E dot dA is proportional to E dot dA is proportional to the number of lines passing through dA vector. We said proportional. Why? We can't count exactly. Is that okay? We can't count exactly, isn't it? It all left to our choice. Remember, electric field is a kind of that's our choice, isn't it? Yeah. Now let me slowly get into Gauss law. So later I'll give some more arguments. Okay. So now let me do in in this way. Later let me argue. So this is the definition of flux. Okay. So whenever you have a flux, so through some surface, you better write E dot dA. Okay. Suppose E vector and dA vector have got same angle. The angle between E vector and dA vector is same. Then what would happen? I can write this one as mod A, mod dA cos of the angle. Am I right? Suppose throughout the surface, electric field is same, angle between them is same. You can take both of them outside, isn't it? Suppose my first example, I can take electric field as well as cos theta outside, integral of dA vector. What is this one? Integral of dA vector? That's a total area, isn't it? That's the total area. That's what your earlier formula. Is that okay? So that's how it works for a special case. But that is the most general equation. This is the flux through the surfaces. You have to read like that. Okay. You better to put S here, capital S here. Remember, sometimes we are going to use this one. Not sometimes. Now, let me take that example. So, E bar dot dA bar. What is the difference between these two? This should be closed surface area. Is that okay? For closed surface area, you have to put one more circle here. Okay. For open surface area, you have to leave it as it is. Okay. That is the accepted notation. So don't make any mistake. If surface is open, don't unnecessarily so encircle that one. If surface is closed, don't forget to do like that. Okay, be careful. Closed surface area. Suppose a spherical surface, closed surface area. Is that okay? Open surface area. Example, suppose your ice cream cone. That's an open surface area. Am I right? It's open one side. Suppose a hemispherical bowl. So that's also open surface area. Am I right? So here one problem comes. In case of open surface area, suppose if I take let me take hemispherical bowl, open surface area. Am I right? So now, what is the direction of dA that you have to choose? Or any surface, look at here, you have a surface here. So you got two perpendicular directions. In which direction you have to choose area vector? Direction? Why? What the logic? What the logic to choose? I mean, if it is not along the field, then what will you choose? Are you getting my point? I have a vector field here, uniform vector field. Let me take that idea. Okay, I have a so planar area here. Okay, now I got two choice. One is this direction, other is this direction. Am I right? I got two choice of defining area vector. Which one you are going to choose? One, I mean, so now this this vector and this electric field vector, the angle is more than 90 degree. Am I right? This vector, this area vector, and this electric field angle is so one is acute angle, other one is obtuse angle. Am I right? So this will give negative flux, this will give positive flux. Are you getting my point? Cos of obtuse angle, I think that's less than 1. Am I right? Sorry, negative, isn't it? So this area vector. So I mean, so electric field and this area vector, this has got obtuse angle, isn't it? This has got acute angle. Then obviously, if you choose like this, you will get positive flux. If you choose like this, you will get negative flux. But it doesn't matter, isn't it? Number of field line that we are trying to count, it doesn't matter actually. Is it okay? But when you connect this one to the theorem, I think Stokes theorem or Gauss theorem, that convention will come. You have to choose your area vector property. Is it okay? Right now, we don't have any convention. For open surface, we don't have any convention. Is it okay? To choose this dA vector, you can choose either. Look at here. So in case of this hemispherical ball, you can choose your dA vector like this, or you can choose your dA vector inward. Isn't it? You got two choice. You can choose in any way. So if you choose in one way, you may get a total flux positive. If you choose in other way, you may get total flux negative. It doesn't matter. Magnitude will be same. Okay, magnitude will be same. So that's why whenever we write that open surface integral, that ambiguity remains. How to choose your area vector, dA vector. Okay, that ambiguity remains. Okay. So, but when you connect that one to theorem, I think which theorem? Stokes theorem, isn't it? When you connect that one to Stokes theorem, there the let me just discuss that one. The convention comes. Okay. Then you have to follow the convention. Look at here. But if I have closed surface area, okay, I don't have to take sphere, isn't it? So it is very conventional again. Okay, it's very conventional. We don't have logic over it. Okay, that to choose your area vector, dA vector outward from the volume. So one closed surface will produce one volume. Am I right? Inside that one, there will be one region, isn't it? So closed surface always defines one region, one volume, isn't it? So now it is a convention that to choose your area vector outward from that volume, isn't it? It can be of any shape. Remember, it is always convention to choose that area vector outward from the region. Okay, so I mean wherever it is that area vector, you have to choose this one dA vector outward from that region. So again, you have to ask question why we have chosen that convention. Okay, so now that is to make outward flux positive, inward flux negative. Look at here. Let me take the simplest example. Suppose I have a charge Q here plus Q here. Okay. Now obviously electric field lines are going like this. Am I right? Now if you just take a dA vector, if you take dot product with electric field, what would you get? That's acute angle. You will get positive. So the same thing will happen throughout the surface, and you are adding all of those positive quantities, you are getting net flux positive, isn't it? Suppose if you have chosen your area vector inward to that region, what would happen? Look at here. This is suppose if electric field is like this, dA vector like this, then it's 180 degree or obtuse angle. It not need to be 180 degree, remember, obtuse angle. Then look at here, negative flux. So when you integrate throughout the region, so I mean throughout the surface, you will get net negative flux. Am I right? So our way, our idea is to make outward flux positive, inward flux negative. To make outward flux positive, you have to choose your area vector outward from that region. You can just think over it. Just draw that one and think over it. To make outward flux. When you talk about outward flux, wait a second. Only for closed surface. For an open surface, outward flux is meaningless. Am I right? I have one suppose I have some electric field lines here or some field line, isn't it? For an open surface, outward flux doesn't have any meaning, isn't it? Because open surface will not define any region, isn't it? So which is outward, which is inward? You may feel like it is inward, am I right? Just go here, this is outward, isn't it? When it passes through that one, it is outward, isn't it? Or, so let me call this one inward. So everything will be confusing, isn't it? For open surface, inward flux or outward flux, it is meaningless. Only flux. Okay? And you better talk about magnitude, because again ambiguity comes. How to choose dA vector, isn't it? dA vector either this direction or this direction. That's why for open surface, we can't define inward flux or outward flux. That's meaningless. Or, so this is a curved one, you may have some confusion. Suppose if you have a planar surface here, that's also open surface, am I right? Now inward flux, outward flux is meaningless. Only flux is flux through that area. Only that has a meaning, isn't it? So, but when you talk about closed surface area, now outward flux means net field line going out from that region. Okay, because that closed surface area will define one region in, it will define one volume, am I right, in a space. So that's why. So field line, which if there are net outgoing field line, how to say? So if field lines are going outward from that region, we can say outward flux, because so by saying field lines are going outward, and if a field line are going inward to that region, isn't it? We can talk about the region that will be inward flux. Okay. So this idea of choosing your area vector outward from the region of the closed surface is to make outward flux positive, inward flux negative. So write that sentence. So choice of or choosing dA vector, outward from the region of a closed surface, and that dA vector should be perpendicular to that patch. Okay, again for any surface you have two perpendiculars. That is our one is our choice. Am I right? For any patch you got two perpendicular. One is like this, other is inward. Am I right? You heard the sentence? Choosing dA outward from the region of a closed surface, choosing dA vector outward from the region of a closed surface is to make outward flux positive, you better write net outward flux positive, and net inward flux negative. Okay, suppose if you had, now this is our convention. Now onwards, whenever you have closed surface, you have to take your area vector outward from that region. Okay, suppose if I had negative charge, then what would happen? Isn't it? Now you have a field line which are going into that one, isn't it? Now look at here, your area vector is like this, but your electric field is like this. Then cos 180 degree or cos obtuse angle, you will get negative. When you add, you will get negative flux. The total flux will be negative. Is that okay? Because that is inward flux. our field lines are going into that region, let's say inward flux, okay. So that convention is because of that. Yeah, after understanding this, I mean, whenever you talk about closed surface, you have to write closed surface integral of E bar dot dA bar. You can call it as net flux then, isn't it? Net flux. If that net flux is positive, that is outward one. If that net flux is negative, then that is inward one, okay, according to our dA vector convention, okay. Now look at here. Now let me first prove Gauss law in an integral form, then we shall come again, okay. Now for a time sake, let me assume this electric field line property. Are you getting my point? Let me assume this electric field line property, or even after proving that one, so I can show some electric field line property. Look at it, I can show that one. Yeah, those integral and differential forms are equivalent. So that's why once you prove that one, you can talk about electric field again, okay.